CESA-2 is a computer software program primarily used in the field of piping stress analysis for the design and evaluation of piping systems within various industries, including oil and gas, petrochemical, chemical, power generation, and more. Developed by Hexagon PPM, formerly known as Code Incorporated, CESA-2 has been a staple tool in the engineering and construction sectors for decades. In this comprehensive guide, we will explore CESA-2 software in great detail, covering its history, features, applications, analysis methodologies, and much more to equip you with a thorough understanding of this software. CESA-2 was initially developed in the late 1980s by Code Incorporated, a Texas-based engineering software company. Over the years, it has evolved into a comprehensive and widely used tool for piping stress analysis. In 2005, Code was acquired by Hexagon UB, a global provider of information technology solutions. The software has since been developed and enhanced under the Hexagon PPM brand. CESA-2 is designed to address the critical engineering task of analyzing the stresses and deformations in piping systems. These systems are essential components in various industries, carrying fluids and gases under different operating conditions. Ensuring the integrity and safety of these systems is paramount, and CESA-2 plays a pivotal role in achieving this. CESA-2 is renowned for its robust feature set, which includes modeling tools. The software provides tools for creating a detailed 3D model of the piping system, including components such as pipes, fittings, valves, and supports. Analysis capabilities. CESA-2 performs both static and dynamic analysis, assessing factors such as thermal expansion, pressure, and seismic forces. Load cases. Users can define multiple load cases, considering various operating conditions and scenarios. Code compliance. The software ensures that designs adhere to industry standards and codes, such as ASME B31.1, ASME B31.3, and many others. Intuitive interface. CESA-2 features a user-friendly graphical interface that simplifies the modeling and analysis process. Extensive material database. It offers a comprehensive library of materials commonly used in piping systems. Reporting and documentation. The software generates detailed reports and documentation for design validation and regulatory compliance. CESA-2's user interface is designed with engineers in mind, providing a visually intuitive workspace. The software uses a Windows-based graphical interface, making it accessible to users with varying levels of expertise. Key components of the interface include the piping model view, analysis input dialogues, and result visualization windows. Piping stress analysis is the engineering discipline that assesses the behavior of a piping system under various loads and operating conditions. It ensures that the system can withstand stresses, strains, and deformations while maintaining its structural integrity and safety. Stress analysis is crucial for several reasons. Safety ensures that the piping system can operate safely without failure. Efficiency optimizes the design for material usage and minimizes costs. Compliance ensures that designs conform to industry standards and codes. Reliability predicts potential problems before they become costly issues. Legal requirements. Compliance with regulatory authorities and safety standards. Various industry codes and standards govern piping design and analysis, and CESA-2 supports compliance with many of them. Some prominent standards include ASME B31 series, American Society of Mechanical Engineers codes for pressure piping covering various industries. API codes, American Petroleum Institute standards for the oil and gas industry. ISO standards, International Organization for Standardization codes for international applications. EN-codes, European norm codes for European applications. Other regional codes, depending on the project location, other regional codes may apply. Piping systems are subjected to several types of loads, including thermal expansion due to temperature changes, pressure resulting from fluid or gas flow, weight from the piping itself and its contents, seismic and wind forces, external forces from environmental conditions, vibration, oscillatory forces that can lead to fatigue failure, dynamic loads resulting from rapid changes in operating conditions. Piping stress analysis can be categorized into different types, such as static analysis, analyzes stresses and displacements under steady-state conditions. Dynamic analysis, considers time-dependent loads and transient conditions. Modal analysis, determines natural frequencies and mode shapes. Response spectrum analysis, evaluates response to seismic forces. Time history analysis, simulates transient conditions over time. The first step in using CESA2 is creating a detailed 3D model of the piping system. This includes defining the geometry, components, and material properties of the pipes. Users can import piping layouts from CAD software or create them from scratch within CESA2. Setting up boundary conditions is critical. This involves defining restraints and supports at fixed points in the model, specifying where the piping is anchored, and how it is constrained from moving. Boundary conditions help simulate real-world conditions accurately. Users define load cases to represent different operating scenarios, including variations in temperature, pressure, and external forces. Load cases encompass all the conditions under which the piping system must be analyzed. CESA2 offers various analysis options, including the type of analysis, static, dynamic, etc., the method of solving, for example, finite element analysis, and considerations for nonlinear behavior. Once the model is prepared, and load cases and analysis options are defined, users initiate the analysis run. CESA2 solves the equations governing the behavior of the piping system and calculates stresses, displacements, and other relevant parameters. After the analysis run, users can review the results in CESA2's graphical interface. The software provides visualizations, plots, and reports to help engineers interpret the data and make informed design decisions. Modeling begins with defining the geometry of the piping system. Users create the layout of pipes, fittings, flanges, valves, and other components. Accurate geometry is essential for realistic stress analysis. CESA2 includes a library of standard pipe components, including elbows, T's, reducers, and more. Users can select and place these components in the model, specifying their dimensions and properties. Material properties, such as Young's modulus, Poisson's ratio, and thermal expansion coefficients, must be assigned to each component. CESA2 provides an extensive material database, and users can add custom materials when necessary. Defining restraints and supports is crucial for accurate analysis. Engineers specify how the piping is anchored and constrained, taking into account the real-world conditions at the installation site. Load cases include temperature, pressure, and other operating conditions. These factors are input into CESA2 to simulate the effects of various scenarios on the piping system. External forces and loads, such as wind, seismic activity, and dynamic forces, are applied to the model to simulate real-world conditions. Users define these loads as part of the analysis setup. Static analysis is the most common type and is used to assess stresses and displacements in a piping system under steady-state conditions. It considers factors like thermal expansion, pressure, and weight. Engineers often perform multiple load cases to account for different operating conditions. Dynamic analysis is essential for systems subjected to rapid changes in operating conditions or transient events. It assesses the response of the piping system to time-dependent forces, such as water hammer or relief valve discharge. CESA 2's dynamic analysis capabilities are particularly valuable in industries like power generation and chemical processing. Modal analysis determines the natural frequencies and mode shapes of the piping system. Identifying these modes helps engineers avoid resonance and structural failures caused by excessive vibrations. This analysis type is crucial for systems sensitive to dynamic forces. Response spectrum analysis is used to evaluate the response of the piping system to seismic forces. Engineers input a seismic response spectrum, which represents ground motion, and CESA 2 calculates the system's response to these forces. This is crucial in earthquake-prone regions. Time history analysis simulates transient conditions over time. It is commonly used in situations where the loadings vary rapidly, such as during startup or shutdown of a process plant. CESA 2 can simulate how the piping system responds to these changing conditions. CESA 2 provides detailed stress analysis results, including axial stress, hoop stress, and shear stress. Engineers review these results to ensure that stresses remain within allowable limits defined by industry codes and standards. Displacement analysis results indicate how much the piping system deforms under various loads. Excessive displacement can lead to misalignment and structural issues. CESA 2 helps engineers identify areas of concern and make design adjustments. Nozzle analysis is a critical aspect of piping stress analysis, especially for equipment connections like pumps and vessels. CESA 2 assesses the loads on nozzles and provides calculations for their reinforcement if needed. For systems in regions prone to high winds or seismic activity, CESA 2 evaluates the effects of these forces. Engineers can assess how the piping system responds to wind-induced vibrations or seismic events and make design improvements accordingly. Fatigue analysis is vital for systems subjected to cyclic loading. CESA 2 calculates fatigue life and helps engineers predict when and where fatigue failure might occur. This is essential for ensuring the long-term reliability of the piping system. CESA 2 generates detailed reports that document the analysis process, results, and compliance with relevant codes and standards. These reports are essential for regulatory approval and project documentation. The ASME B31 series of codes, published by the American Society of Mechanical Engineers, cover various aspects of piping design, including pressure piping, power piping, and process piping. CESA 2 provides tools to ensure compliance with these codes, such as ASME B31.1 for power piping and ASME B31.3 for process piping. For the oil and gas industry, compliance with API codes is crucial. CESA 2 supports API standards like API 610 for centrifugal pumps, API 650 for storage tanks, and API 661 for air-cooled heat exchangers, among others. In international projects, adherence to ISO standards is essential. CESA 2 can be used to design and analyze piping systems according to ISO standards, ensuring global compatibility. Depending on the industry and location, other codes and standards may apply. CESA 2's flexibility allows engineers to work within the framework of regional and industry-specific codes. In addition to piping, CESA 2 offers specialized modules for analyzing static equipment such as pressure vessels and heat exchangers. These modules enable engineers to assess the integrity and compliance of these critical components. For offshore applications, CESA 2 includes features to address the unique challenges of subsea pipelines and platforms. It considers factors like wave loading, buoyancy, and seabed interactions. The dynamic analysis capabilities of CESA 2 are enhanced in specialized modules. These modules can handle complex transient events and dynamic loads, making the software suitable for a wide range of applications. FETools is an add-on module for CESA 2 that extends its capabilities to perform finite element analysis, FEA. FEA allows for more detailed and accurate stress simulations of complex geometries and loadings. Caesar 2 offers several other modules and add-ons, including those for heat exchanger analysis, expansion joint analysis, and nozzle flexibility analysis. These modules enhance the software's versatility and utility in various industries. Caesar 2 is often integrated with computer-aided design (CAD) software such as AutoCAD or Bentley MicroStation. This integration allows for seamless import and export of piping geometry, streamlining the modeling process. In addition to CAD, Caesar 2 can be integrated with computer-aided engineering (CAE) software for more advanced simulations. This integration enables engineers to leverage the strengths of both Caesar 2 and CAE tools for complex analyses. Caesar 2 can be integrated into overall plant design and engineering systems, facilitating collaboration between piping designers, stress analysts, and other engineering disciplines. This integration ensures that the piping system is part of a cohesive plant design. Convergence refers to the process by which the analysis solution reaches a stable result. Engineers may encounter convergence issues if the model is poorly defined or if the analysis parameters are not set correctly. Troubleshooting convergence problems is essential for obtaining reliable results. Errors in the piping model, such as incorrect geometry or improperly defined boundary conditions, can lead to inaccurate results. Engineers need to carefully review and validate their models to avoid these errors. Interpreting analysis results and understanding their implications can be challenging, especially for complex systems. Engineers must have a deep understanding of piping mechanics and the specific requirements of the industry codes being used. Optimizing a piping system for efficiency and safety requires experience and engineering judgment. Engineers often need to iterate on the design to achieve the best balance between cost, performance, and compliance. Start with accurate geometry and material properties. Ensure that boundary conditions are realistic and representative of the installation site. Consider all potential load cases and load combinations. Carefully define load cases to encompass all operating scenarios. Combine load cases to assess the most critical conditions. Use industry-specific load combinations as per relevant codes. Choose materials that meet code requirements and are suitable for the intended service. Verify material properties and stress-strain curves for accuracy. Cross-check analysis results with hand calculations to validate the model. Use engineering judgment to assess the significance of stresses and displacements. Maintain detailed records of the analysis process and assumptions. Generate comprehensive reports that document compliance with codes and standards. Caesar 2 is widely used in the oil and gas sector for designing and analyzing pipelines, offshore platforms, refineries, and petrochemical plants. It ensures the safe transport of hydrocarbons and compliance with industry regulations. In the petrochemical industry, Caesar 2 is instrumental in designing complex piping networks that transport a variety of chemicals. It ensures the integrity of these systems and helps prevent leaks and accidents. Power plants, including nuclear, coal, gas, and renewable energy facilities, rely on Caesar 2 for designing and analyzing the intricate piping systems that transport steam, water, and other fluids critical to power generation. Chemical processing plants use Caesar 2 to design piping systems for the production and transport of chemicals. The software helps prevent corrosion, leaks, and other issues that could compromise safety and product quality. Caesar 2 finds applications in various industrial sectors, including water and wastewater treatment, pharmaceuticals, food and beverage, and more. Any industry that relies on complex piping systems can benefit from Caesar 2's capabilities. The integration of Caesar 2 with digital twin technology is a growing trend. Digital twins create virtual replicas of physical piping systems, enabling real-time monitoring, predictive maintenance, and performance optimization. The adoption of cloud-based analysis tools is on the rise. Cloud platforms offer scalability, collaboration, and remote access, making it easier for engineering teams to work together on complex projects. AI and ML are being explored to enhance the accuracy and speed of piping stress analysis. These technologies can help automate certain aspects of modeling and analysis. There is a growing emphasis on designing piping systems that are environmentally friendly and energy efficient. CESA 2 may evolve to include tools for assessing the environmental impact of piping systems and optimizing them for sustainability. CESA 2 is an indispensable tool in the world of piping stress analysis. Its role in ensuring the safety, reliability, and compliance of piping systems across various industries cannot be overstated. As technology advances and industries evolve, CESA 2 continues to adapt and meet the ever-growing demands of the engineering community. Despite the emergence of newer technologies, CESA 2 remains relevant due to its versatility, robust feature set, and extensive user base. As long as industries rely on complex piping systems, the need for accurate stress analysis and compliance with codes and standards will persist. CESA 2 is a powerful tool, but its effectiveness depends on the expertise and judgment of engineers who use it. Engineers play a crucial role in ensuring that piping systems are designed, analyzed, and maintained to the highest standards of safety and performance. In conclusion, CESA 2 is more than just software, it's a cornerstone of modern engineering practice, contributing to the safety, efficiency, and reliability of critical infrastructure worldwide. As the engineering landscape continues to evolve, CESA 2 will evolve with it, supporting engineers in their mission to create safe and efficient piping systems for generations to come.